Alright, so let's go through this question. So we have this light shining into the open end of a box. So we don't know what's inside the box, right? So the two LEDs emerging from the box are connected to a sensitive emitter which reads 0. So means there's no current flowing, right? Okay, so a bar magnet is then moved towards the open end. So meaning, okay, so bar magnet is north pole here, south pole here, right? And the needle then suddenly, right, deflect. So I can actually deduce one thing, say, oh, there's some current already. Okay, when the bar magnet stop moving, so now stop moving, right? The needle returns to 0, so no more current. So what is connected to the two LED inside the box? Okay, so maybe I use your option A. So for example, a coil connected in series with a cell, meaning a battery. So if A is the answer, right, by right, the ammeter should always register a reading, meaning there shouldn't be any zero reading of the ammeter. So cannot be A, because they already say, right, at the start, the reading, the sensitive ammeter reads 0. Then after the magnet stop moving, the needle also returns to 0. So there's some moment in time where current is equal to 0. So cannot be a battery that's inside the so-called open end of the box. Okay, so what is the answer? The answer should be a coil only. Okay, why is the coil only? Because you think about this, for example, okay, initially there's no current. Then after, only if the magnet move, right, then there's a current. So why is there a current when the magnet move? Because apparently, right, let's just say inside the box is a coil of wire. So okay, the coil of wire of course is connected to an ammeter. So this is a sensitive ammeter. So imagine, okay, these are all the turns of the wire, right? So according to Faraday's law, because of the change in magnetic flux or magnetic flux linkage, the coil will actually induce a north pole here and of course a south pole here. So how do I induce the north and south? You need to induce a current first. So a current using a right grip rule, apparently, right, you can see that, oh, my current is flowing in this direction. So only when the magnet move, there's induced current, and this induced current, right, will flow to the ammeter, and the ammeter will actually register some reading. Okay, then after that, when the magnet stop moving, north and south, right, okay, so this is the coil of wire. So same thing, this is an ammeter. So you can see that there shouldn't be any induced current because there's no change in magnetic flux. No change in magnetic flux, no induced current. So that's why your ammeter actually register a 0 reading. As what they actually say, return to 0. So that's why the answer is B. Okay, C also cannot be the answer because C, LDR in series with a cell. So if it's a series in a cell, right, it means that there must be current. There must be current always. Always there must be a current. Okay, what about D? A light dependent resistor only. So imagine I have a light dependent resistor. Okay, so I connect. So let's just say, oh, this is the, I think it's light dependence like that. Something like that. Okay, so this is a light dependent resistor. Then I connect to a ammeter. Then I shine light on it. Apparently, then after that I shine light on it, and after that the magnet move, right, there shouldn't be any current at all, even though the magnet move, or even though there's light shining on it. Because when light shines on it, it just actually decrease the resistance. You can decrease the resistance or increase the resistance, but there's no current supply. So means if you connect LDR inside the box, right, the current will always be equal to 0. So cannot be D as well. So the best option is B, a coil only. So a coil, right, there's some area, there's some wires, right. So when the magnet move inside, then there will be induced current. When the magnet stop moving, there will not be any induced current. So that's how we actually solve this question.